Okay, so this is the video that hopefully Greg promised my normal maths class on Thursday when I was off doing GCSE type things, which is the summary of equations of a straight line. And I've done this and I've realised it's going to take at least 2 videos. So this video is going to be all the theory, and the next video will be a full worked kind of solution, or even a pair of solutions talking about how to deal with the questions that you might have seen about straight lines and all the other stuff. First of all, what the hell is the topic of this? Well, if you haven't read the title, we're going to be talking about the equations of a straight line. What is an equation of a straight line? 3 general forms. Y equals mx plus c. This is the one I favour. It's not necessarily the best one. You know, it's always the thing that you're brought up with is the thing that you like best. Where m, the coefficient of x, the number in front of x, is the gradient, and c is the y-intercept. Now, the formula for m is that if you've got any two coordinates x1, y1, x2, y2, you plug them into that formula, y2 minus y1, x2 minus x1. Again, if you're thinking, well, I don't really get that, he's just saying that at me, watch the next video where it will actually, I'll take you through a work solution. One question I always get is, does it matter which one's x1, y1? Does it matter which one's x2, y2? The answer to that is no, but if you choose something to be x1, the other coordinate that's in that pair has to be y1. You can't have a coordinate that goes x1, y2. Right, but it doesn't matter the order, because the way that formula works, if you pick it whichever way around you pick it, and if you pick it one way, it will just be positive, and if you pick it the other way, you'll get 2 negatives, and obviously a negative divided by negative is still a positive, so it doesn't really matter which way around you do it, but just pick whatever you pick for x1, make sure that's the other coordinate, the y coordinate, is also, you've labelled that y1. Here's the second one. I secretly think this is probably better, though I'll never admit it in class and shout at people that use this method, even though it's probably better. Y minus y1 equals mx minus x1. You can see the advantage straight away. You only need one coordinate as long as you already know the gradient. M is the gradient, x1 and y1 is any coordinate on the line. So that's another one. And there's this third one that's generally used in further maths for something. It's a bit worrying because I teach further maths and I still don't know what the hell this is for. Actually, I do know what it's for, but I'm not going to talk about it because it's not relevant to anyone yet, not even the further maths guys that are doing it. When we get there, we'll talk about it. Okay. If there's a solution to 2 simultaneous equations, that's the same thing as saying the lines in the graph meet. So if you were doing simultaneous equations and you got yourself a solution, you can tell that if you drew the graphs of it, they'd meet at least one point. If you also can turn that on its head, if you draw 2 graphs, if you draw 2 lines and you know they meet, that implies you could have solved those 2 as simultaneous equations algebraically, so they mean the same thing. What sort of solution sets could you get? You could get no solutions. If both your equations are parallel to each other, so that means they've got the same gradient, you could get no solutions. They can meet in one place, which is the vast majority of lines. They touch in one place. They don't necessarily have to be perpendicular for that to happen. They can meet each other at all kinds of angles as long as they're not parallel. And the most rare thing of all, and the reason I'm mentioning this is because it turns up in vectors later on this year and a lot more next year, is you could have infinitely many solutions. How the hell does that happen if you've got 2 equations that are actually the same equation? Let me give you an example. If you sketch y equals x plus 2 and 2y equals 2x plus 4, then you'd have the same equation twice effectively, just the second equation has been multiplied by 2. If you plotted both of those, you can do this on Desmos if you want. So just to recap that, y equals x plus 2, 2y equals 2x plus 4, you'd get one of them lying on top of the other one. So that obviously they'd have infinitely many solutions. Every single point on that line is a solution because both lines are on it. Incredibly rare. In fact, you probably won't get that until you start talking about things like when you do vector lines. They turn up there sometimes. Further mathematicians, you've been warned. Also, you guys will be warned for later on. Alright, if 2 equations are perpendicular, if they are perpendicular to each other, their gradients are negative reciprocals of each other. And I think that's where I'm going to stop here, because after this, I just want to go through examples. Example of this would be y equals 3x plus 2 and y equals negative 1/3 x plus 6. First of all, what the hell is a negative reciprocal? A reciprocal, remember, is just 1 over the number if it's an integer, or flip the fraction. So the negative reciprocal of 3 is minus 1/3 here. So if your gradients are negative reciprocals of one another, then the equations are perpendicular. And that's really all I want to say on that, until I actually do you an example. You can see like why I've kind of stopped there. This video is heading up to 5 minutes. And I'll do another example, it'll be 10 minutes. No one's watching my videos for 10 minutes. I've looked at the analytics. You just come here for like short little bursts. So that's pretty much it. And I'm going to stop there. Bye.